Hello and welcome. This is Unit 3, Lesson 4, Pascal's Pride in OUR Curriculum, Integrated 3. Today we're going to learn about multiplying polynomials, also the ability to raise some polynomials, binomials specifically, to powers very quickly using a pattern. So let's start. It says multiplying polynomials can require a bit of skill in the algebra department, but because polynomials are structured like numbers, multiplication works very similarly. When you learn to multiply numbers, you may have learned to use an area model. So here's an area model that's pictured, and basically each rectangle is just the length times the width. So 10 times 10 is what's giving us 100, and you can see there's a tally here on the side of all the different numbers that you would get to add up to 180, 12 times 15. It says you may have used the same idea with quadratic expressions. Area models help us think about multiplying, factoring, and completing the square. So here's a model of x plus 2 times x plus 5. Every single x is pictured here. And here's our answer, by the way, x squared plus 7x plus 10. But we don't have to draw every single individual x and number. In this case, some people like to abstract the area model a little bit to just have sections of area that correspond to lengths of sides. So this is the generic rectangle. And it abstracts what was done in this other rectangle over here. It says, well, you know, there's a, there's an x part, there's a number part. So we'll just make those x parts and number parts all sort of come together. What is the property that all these models are based upon? That is the distributive property. Yep, big D. And in fact, you can even model distributive property with a box. So for example, if you wanted to do 2 times x plus 3, you could just go like this, very simple box, 2x plus 3, and that's 2x plus 6. Now that this is number 2, now that you've been reminded of the past, we're ready to use the strategy of your choice to find the equivalent expressions for each of the following. So we can, for example, use the box here, and we can do x plus 3 and x plus 4, and get x squared plus 3x plus 4x plus 12, and that's x squared plus 7x plus 12. Or what you can do is distribute each of the individual terms like this into the other binomial. So that would be x squared minus 2x, and then multiply the second term 7 times each of the terms in the second binomial, plus 7x minus 14. And then you just add those together, x squared plus 5x minus 14. Each of those is available to you. It's as you choose. It says maybe now you remember some of the different forms of quadratic expressions, factored form and standard form. These forms exist for all polynomials, although as the powers get higher, the algebra may get a little trickier. In standard form, the polynomials are written so that the terms are in order, with the highest powered term first, and then the lower powered terms, so that each term is of a lesser power than the previous. So these are all in standard form because they go highest power to lowest. Like on this quartic right here, it goes 4, 3, 2, 1. We don't see the 1, but it's there. And then finally, on 4, that's actually 0. You could think of that as x to the 0. So it does go 4, 3, 2, 1, 0. Hopefully, you also remember that you need to be sure that each term in the first factor is multiplied by each term in the second factor, and the like terms are combined to get standard form. You can use area models, boxes, or mnemonics, such as FOIL. There's an interesting word, right? Mnemonics. So we're taking the first letter of each thing we do and making it a word, first, outer, inner, and last, to help you organize. Or you can just check every time to make sure you have all the combinations. And of course, it gets more challenging the higher powered the polynomials are. But the principle is the same. It's all based upon the distributive property. Tia's favorite strategy for multiplying polynomials is to make a box that fits the first two factors like an open area model. So she sets it up like the way you see here. Here's your x plus 2 over here. And then she puts her x squared minus 3x. Oops, let's try that again. We want the highlighter. And I just lost the highlighter. There we go. X squared minus 3x plus 5 is right here. And so we just multiply like crazy. X times x squared, negative 3x squared, 5x, 2x squared, negative 6x, and 10. Making sure that we do not change the exponents unless we multiply by another exponent. Then we have to take it out of the box. There's only 1x cubed. The like terms tend to be organized like this with diagonals. So that would be negative x squared and negative x, and finally plus 10. There's our standard form. It says try checking your answer by graphing the original factored polynomial and then graphing the polynomial that is your answer. If the graphs are the same, you are correct. So that's something you could do in Desmos. We're not going to do that here. Tehani's favorite strategy is to connect the terms she needs to multiply in order like this. So this is really just a visual distributive property. And so let's try this. She's going to multiply x times x squared and get x cubed, x times 4x and get 4x squared, and x times negative 2 and get negative 2x. Then she's going to come back with negative 3 and multiply it times x squared. So negative 3x squared, then negative 3 times 4x, and finally negative 3 times negative 2, or positive 6. Let's put our like terms together. Only 1x cubed. There's 4x squared minus 3x squared is 1x squared. Negative 2x minus 12x is negative 14x, and then a plus 6. So there we go. Which way did you like better? It says use the strategy of your choice to multiply each of the following expressions. Check your work by graphing and make any needed corrections. So let's see here. On 6a, I'm just going to give you the answers to these. You should get x cubed, 4x squared, minus 8x minus 15. And over here, you should get 2x cubed plus 2x squared minus 11x minus 2. And finally, x cubed plus 3x squared minus 4x minus 12. Of course, I'm going to assume that you actually work those out and you're just using that to check your answers. All right, let's see what else we've got here. When graphing, it's often useful to have a perfect square quadratic or a perfect cube. Sometimes it's also useful to have these functions written in standard form. Let's try rewriting some related expressions to see if we can use some useful patterns. So it says to go ahead and multiply both of the following expressions using the strategy of your choice. So I'm not going to pick one strategy over the other on this. I just want to get you going with the answers. You pick the strategy. This will be x squared plus 2x plus 1. And this other one will be x cubed plus 3x squared plus 3x plus 1. Check your work by graphing, etc., etc. And then number 8. Now, looking at the pattern, and we already know the answer here. And we know the answer here. And then look at the numbers only on that last column. So what they've done is they've written it into a triangle. And if you notice, every number comes from the 2 that are above it. So for example, this 3 comes from the 2 and the 1 above it. They're added together to give you the 3. So the next line is going to start with a 1. Then we're going to add 1 and 3 to make 4, 3 and 3 to make 6, 3 and 1 to make 4, and then there'll be a 1 on the outside. Let's do one more at the end. X plus 1 to the 5th. So let's write this one. X to the 4th plus 4x cubed. Notice the power is going down. Plus 6x squared plus 4x plus 1. The power of x went down from 4 to 3 to 2 to 1 to just not even there. So the next one's going to do the same, but it's going to start at x to the 5th. X to the 5th, and then let's work out the numbers in front. So 1, 5, 10, 5, not 5, 10 again, 5, and then 1. 1, 5, 10, 10, 5, and 1. So 1x to the 5th plus 5x to the 4th plus 10x to the 3rd plus another 10x squared plus 5x plus 1. Some enterprising young mathematician noticed a connection between the coefficients of the terms and the number pattern known as Pascal's triangle. This was named after Blaise Pascal, French mathematician who lived a couple hundred years ago. Put your answers from problem 7 into the table and compare. And so, yeah, they work. That's where we got them from. Describe the relationship that you see. The coefficients match. Remember what a coefficient is. It's the number in front. Coefficients match. It could save some time on multiplying the higher power polynomials if we could use Pascal's triangle to get the coefficients. First, we would need to be able to construct your own Pascal's triangle and add rows when you need to. Look at the triangle, and see if you can figure out how to get the next row of the triangle using the terms from the previous row. Well, I already explained that to you. And we did x plus 1 to the 4th. Okay, so that's done. Now you can check your Pascal's triangle by multiplying out x plus 1 to the 4th and comparing the coefficients. Hint, you might want to make your job easier by using your answers from problem 7 in some way. Put your answer in the table. Well, we've already kind of done that. But what I think they're suggesting is that you could take x plus 1 squared and do it times itself again, and that could be a shortcut, kind of a shortcut, because, well, that would be a 9 by 9, or a 3 by 3, which would be a 9 box, like this. And then we know that each one of these is x squared plus 2x plus 1. So x squared 2x1, x squared 2x1. This is one of many possible ways to do this, by the way. You don't have to do it this way, but this would be x to the 4th, 2x cubed, x squared, another 2x cubed, 4x squared, 2x, x squared, 2x, and 1. And when you take them out of the box, you get x to the fourth. You got 2x cubed twice, so 4x cubed. You got 4 and 1 more x squared, so 6x squared. And then you got 2x and 2x makes 4x, and then just the plus 1. So that's exactly what we put in the table. You notice it's just going down in powers as you go along. Okay, so describe how to get the next row in Pascal's triangle using the terms in the previous row. Well, you got to start with 1, the number 1, and then each new number comes from adding the 2 above it, the 2 numbers. Above it. Complete your next row and use it to find the standard form. Well, we did that already. Pascal's triangle wouldn't be very handy if it only worked to expand powers of x plus 1. There must be a way to use it for other expressions. The table below shows Pascal's triangle in the expansion of x plus a. So you see powers of x go down, while the powers of a go up as you go from left to right. That's what I noticed. Powers of x go down, starting at 4, and powers of a come up. Starting at, well, it would be starting at 0 because you don't even see the a, and then suddenly the a pops up. So it must be starting at 0. Use Pascal's triangle method to find the standard form for x plus 2 cubed. So we're going to go, here's Pascal's triangle, right? It goes 1, 3, 3, 1. That's the line we're going to use for cubing. So x cubed, then there's the 3 from the table, then x goes down to 2, and the number 2 comes up to the first power, to the 1. Plus another 3, x goes down to the first power, 2 comes up to the second power, and then finally it ends with a 1. X has disappeared, and 2 has come up to the third power. So it's x cubed, 6x squared. The 3 times 2 squared would be 3 times 4, 12x, and then plus 8. And there you go. And we could check it by multiplying it out the long way. It'll work. Okay, here's some other ones that says use any method. Well, I'm going to show you Pascal's triangle because that's what the lesson is about, right? So each of these first 2 is cubed and then a fourth power. So the first 2 are going to use that pattern 1, 3, 3, 1. So it's going to go x to the third and then 3x squared times 3. See, 3 has made its appearance now. Then another 3 from the table, x goes down to 1, and 3 gets squared now. And finally, we end with the 3 being cubed. That's x cubed plus 9x squared plus 27, 3 times 9, x plus 27. Okay, part B. Now, what do we do if there's a negative in there? Still start with x cubed. And then we got to have, I'm just going to write each term with a plus, and I'll throw the negative in with the 2. So plus x squared times negative 2 plus, oops, I forgot something, didn't I? Forgot the 3. 3x squared times negative 2 plus another 3x with a negative 2 squared. And then finally, negative 2 cubed. So it goes x cubed minus 6x squared plus 3 times 4, 12x minus 8. That looks very similar to something we did before, right up here in number 10. Except that one was a plus, so it had positives all the way through. This one has a minus, so it's alternating between positive and negative. Okay, C has the pattern 1, 4, 6, 4, 1. Is that right? 1, 4, 6, 4, 1. Let's look up here in the table. 1, 4, 6, 4, 1. Yep, that's it. So we're going to start with x to the 4th plus 4 x to the 3rd, and 5 makes its appearance, and 6x squared, and 5 now gets squared, and 4x, and 5 now gets cubed, and 5 now to the 4th. So x to the 4th plus 20x to the 3rd plus, let's see, you got 5 squared is 25 times 6, 6 quarters, that's $1.50, so 150 x squared plus 5 cubed is 125, and you have 4 of them. 2 of them would make 250, so 4 of them would make 500 x. And let's see, 5 to the 4th is 625. But it sure beats doing it the long way, definitely. Okay, so let's see if there's a few takeaways that we can put down here. Let's put down this major one. A plus b to the n is not going to be a to the n, b to the n, except when n equals 1, all right? So there's a lot of middle things that are supposed to be happening there. You can always check with a graph. That's helpful. Don't forget, in general, this is before Pascal's triangle, combine like terms. And you can use the box to help you. That box is really helpful because an empty box says, I got to do something. So you hopefully won't forget to do all of your multiplications. So we put Pascal's triangle in the vocab, right? This unique triangle starting with a triangle of ones at the top. And it helps us to do a binomial expansion. Okay, I hope that helped. We'll see you next time.